An important ability that we have to have in understanding motion is being able to graph motion. And to graph motion, we're going to look at three different types of graphs: position versus time, velocity versus time, and acceleration versus time. So common position versus time graphs that we'll see would look something like this. And what we need to do is understand what these types of graphs are telling us. Now, if we're to look at a position versus time graph, and let's look at this red line first, position versus time graph can tell us some information. If we were to look at this graph, from this position, we'll call that 1, to position 2, this object traveled a distance over a time. So the distance that they traveled, and we're going to say actually the displacement that they traveled, is that y rise. So from 1 to 2, they rose a certain displacement, and then the time is the horizontal movement in my graph. And so from this, we can see that the slope of this is going to be my velocity. And that's because that is displacement divided by time. So the slope of a position time graph is going to be velocity. Now, when we're looking at the blue graph, you can't really get an overall slope because we are accelerating. But what we can do is we can look at the slope as it's moving. If we took the tangent line here and here and here, we can see that this slope is getting steeper and steeper and steeper. So that's going to show something that is speeding up. So when we're looking at graphing motion, the main idea that we have to understand is that anything that is moving in this direction is in the positive direction with a positive velocity. Anything that is moving downward is going to have a negative velocity. So not only can we tell how fast something is going by the slope, but we can tell the direction by the direction that is moving. So even though this blue one is starting in the positive region, it is moving in the negative direction the entire time. So these are positive positions, and these are negative positions. And the red one, even though it starts in the negative position, it is moving in the positive direction the entire time because it has a positive slope. Next, we're going to look at the idea of a velocity versus time graph. So this type of graph doesn't tell us where things are, but it's going to tell us the velocity and how things are actually moving. So let's look at our position time graph again, which looked like this. We had our red object moving up in the positive direction, but it stayed at a constant velocity. So because of that, it's going to produce a velocity that looks something like this. Notice anything above my x-axis are going to be positive velocities. Anything below are going to be negative velocities. And so the red object had a positive velocity, it moved in the positive direction the entire time, but it maintained a constant slope or a constant velocity. So here we have a constant positive value for my velocity. So think of this as, positive 3. The entire time, that value is at positive 3. For my blue object, we start with an initial slope really close to flat, which would be 0. And then that slope again is getting steeper and steeper and steeper as time is going. So my velocity there would look something like this, okay? Where this would be 0 velocity, -1, -2, -3. Don't worry about the scaling, be a little bit different, but we can see that -1, -2, -3, we are speeding up, okay? Now, with this, we need to understand two concepts. We need to understand what does the slope tell us. We also need to understand what does the area tell us, okay? So for the slope, that again is rise over run. So we're going to use the blue one as our example. Rise over run from position 1 to position 2. Our rise is our change in velocity. All right, so we started out at some velocity here, and this is how much our velocity changed. So our slope is change in velocity. And then our run is time. Again, how much time went by from position 1 to position 2. And so because of that, we're going to say our slope actually tells us our acceleration, right? Which is measured in this case as, let me move that over. It's measured So that's acceleration measured in meters per second squared. So that's written as, meters per second divided by seconds. That's how we go from here. Change in velocity, which is meters per second, divided by seconds, gives me meters per second squared. Now, the other concept is the area. And notice we didn't do area on a position time graph. That's because we don't care about it on a position time graph. But the area would be this area right here underneath my graph. Now, if we look at how would we find that area? Well, area is length times width in terms of a box. So in this case, my length is this from here to here, and that is time. So my area is time multiplied by my width. My width of my box would just be from here to there, from the x-axis to the top of the curve, and that would be my velocity. And if we did that, for my units, that's seconds multiplied by meters per second, or seconds to the -1. That's going to cancel out the seconds, and all I'm left with are meters. And so the area of a velocity time graph is going to be my displacement, okay? It's going to tell me how far I traveled, or how far I moved, and in what direction, but doesn't necessarily tell me where I am. It just tells me how far I went. Okay, so notice it doesn't say, you went from negative to positive. It just says I traveled a total distance of maybe 10 meters. Now, if we're going to try to find the area for the blue line, it would be this area here. Okay, so to find that area, we would have simply that shape of a triangle, which would be 1/2 times the time times the velocity. Right, so that's how we would find that one there. So if we have a rectangular shape, we can just use length times width. If we have this shape here, we can use 1/2 times base times height. Both of those are going to give me my displacement. Notice this one up here would be a positive displacement. This one here would be a negative displacement. And that makes sense because look, I went in the negative direction. So I should have a negative displacement. The last graph we have to understand is something called an acceleration time graph. And looking at acceleration time graph, we're going to use the information just like we'd use the information from a position time graph to make our velocity. We're going to use the information from a velocity time graph to make our acceleration. Because remember, the slope of a velocity time graph is our acceleration. Okay, so how can we use that? Well, if we look at our red graph here, our red graph has 0 slope. It's not accelerating, it's not increasing or decreasing its speed, so our acceleration time graph would simply be 0. It would be on that x-axis. Our blue graph then has a negative constant slope, which must mean it has a negative constant acceleration. So we're going to have a graph that looks something like that, right? And just like for the other graphs, we're going to be able to understand a few things. Now with this, the slope of this graph is something called a jerk. But we are not going to we don't need to really learn about that. Okay, so it's not something that's important. However, we do need to understand the area of this graph. Okay, so again, for this, if we were to find the area underneath our curve, for this, it would simply be a rectangle. So it'd be length times width, right? Our length would be time, and our width, multiplied. Our width would be our acceleration, right? And what does that mean in terms of units? That's seconds multiplied by meters per second squared. And so in doing that, we can cancel out one of these seconds with that, and my units that I would be left with would simply be meters per second. So the area is our change in velocity, okay? And this is important to tell us. It doesn't tell us how fast we're going, okay? It simply tells us how much our velocity changes. So that's what that area underneath that graph tells us. So in review, we need to understand For a position time graph, we need to understand what the slope is telling us, because that slope tells us our velocity and can help us build that next graph. So our slope tells us our next graph. This, we have a decreasing slope, but in the positive direction. We have an increasing or steeper slope in the negative direction, so we're able to produce a graph that looks like this. In this case then, what does our slope tell us of our velocity time graph? It tells us our acceleration. So notice that the slopes tell us the next graph that's going to be produced. For our velocity time graph, we have a negative constant slope, so we have a negative constant acceleration. We also need to understand then the area and how that can work backwards. So the area of an acceleration time graph can tell me my change in velocity, so it can help me understand this graph here. And the area of a velocity time graph can help me with my displacement or my change in position. Okay, which can help me understand this graph here. So notice, position time graph, we only worry about the slope. Acceleration time graph, we only worry about the area. Velocity time graph, we should be able to do both slope and area. And this is important to understand that in terms of finding slope, we're finding the derivative. Okay, and finding the area, we're finding the integral. Oopsie. So, in terms of how we can relate that to our calculus class or math class, right, the derivative is simply going one direction, and mathematically, the integral is going in the opposite direction. And again, I pull our attention to the idea that these graphs do not look the same, and they should never look the same. A position time graph will never look the same as the velocity, and acceleration will never look the same as our velocity. The only time where you might get a graph that looks something of the same is if we have zero position, zero velocity, zero acceleration.